So average angular acceleration will be change in the angular velocity by the time interval in which we have done that change. Just this time interval is going to be a finite one. Instantaneous angular velocity will be limit delta t tending to 0, delta omega by delta t, and by definition we know it will be d omega by dt. Now what we have is, like the way we were finding out the direction of our angular displacement or the angular velocity, the direction of the angular displacement or the angular velocity or the angular acceleration, all is given by the right hand rule. And how to apply that, all of you got it now? So you fold or you curl your fingers in the sense of rotation. In doing so, whichever way the right hand thumb points, that way will be the direction of that vector. And in whatever sense we are going to fold the fingers or curl the fingers, that is the sense of rotation, and that will be the sense of that particular quantity will be. So that we have seen already. I don't need to explain that thing again. Now, just like earlier, whenever A was constant, we were able to write few things. No? Same way, when alpha is constant, or before that, one more thing. You remember that one, no? In 1D or even in 2D, what we were writing it down, the acceleration as dv by dt, no? And then we multiplied it with dt and dt, sorry, dr and dr, and then we did something. You remember that or not? So I will exchange their denominators. So what we get is dv by dr into dr by dt. And dr by dt we can write down as velocity. So what we can do, the acceleration we can write down as a into v dv by dx. Similar to that, here also we can do such kind of thing. For example, if I write down alpha to be equal to d omega by dt, then I will multiply by d theta and d theta. So what we get is d theta by dt into d omega by d theta, where d theta by dt is going to be omega only. So alpha I can write down as d omega by d theta. That is very much similar to the thing that we did earlier. Now, whenever I have alpha to be constant, so I can use the equations that we had earlier, that was v equals to u plus at. Instead of that, I'll write down omega final to be equal to omega initial plus alpha into delta t. Next, we had v square equals to u square plus 2as. So here also we'll have omega final square equals to omega initial square plus 2 alpha into delta theta. And then we have s equals to ut plus half at square. So here we'll have change in the angle will be equal to initial omega into t plus half alpha into delta t square. Correct. And whenever we had a constant, the average velocity was equals to initial plus final divided by 2. No? Correct. So here also we are going to have that average velocity will be initial plus final divided by 2. Copy this thing simple only.
Sir, are these cases possible only alpha is constant?
Alpha is constant, is correct. We can prove it also if you want. I can just prove one of them. This one I raise you must be knowing also. So if I have suppose alpha constant, so what we can do, I can write down our alpha to be equal to d omega by dt. So d omega I can write down as alpha dt. So what you will read this statement or this mathematical equations d omega equals to alpha dt is, it is the change in the omega that will happen in a small time interval dt. So I'll integrate both the sides. Suppose if I integrate it from 0 to t, when at 0, the initial angular velocity omega initial, when at t, final is omega final. Integrating left side will give us omega final minus omega initial. Alpha being constant can be taken out, will be alpha dt. 0 to t, it will become alpha t. No? So what we get is omega final is going to be equal to omega initial plus alpha into t.
Like v square minus u.
Yeah. So next, what I will do, omega, what I have is at any point of time, I can write down as initial omega plus alpha into t. And that omega I can write down as d theta by dt. That will be omega initial plus alpha into t. You throw dt to the other side, then you integrate both the sides. Omega initial plus alpha into t. dt 0 to t, 0 to theta. So it will give us theta equals to omega initial t plus half alpha into t square. That is how we prove the second one. Third one, similar proof only, nothing different. Just I will use this equation. So what we have is omega d omega equals to alpha d theta. Then I integrate both the sides. When theta 0 in the beginning, omega is omega initial. When theta is theta, suppose the omega final is omega final. So integrating left side will give us omega final square minus omega initial square by 2. That will be alpha into theta. So what we get is omega final square equals to omega initial square plus 2 alpha into delta theta. So copy this thing everyone. After copying, tell me. This thing I could have told later on, but I'm telling in the beginning because many people are absent today.
Circular motion chapter, sir.
Circular
System
motion
of
chapter only.
particles.
Main thing I have not started, except the thing that I did in the last class. Is easy thing only that you can understand easily. Thing where people will be getting stuck that I was going to start. Let's see whether I can start that or not. 18, 16 people came out of 22. 6 absent still. Okay, copy this thing. After copying, tell me. Okay, I can take a new page now.
Yes, sir.
Yes, sir.
Let's try one question. Simple only. So what it is given is a solid body rotates about a stationary axis starting with the initial velocity omega naught and angular deceleration whose magnitude is k into root omega. Find the average angular velocity over the whole time of rotation. It means they are asking us the average angular velocity in the time in which it is going to be coming to rest. So it is starting with some initial velocity, and then acceleration is applied on it, which is going to reduce the speed, which is deceleration. So what we have to do is first we have to determine at what time the velocity will become zero, so that I will know for what time interval we have to find the average velocity. Okay, and then we will find in that given time how much the angle it has covered, so that we can find the average angular velocity. Average angular velocity will be the angle that it covers divided by the time interval in which it covers that. No? And what it is given to us, alpha, which is the acceleration, is in terms of omega. Correct. So first we'll need to know how omega will be changing with time, so that I can find when omega will become zero to determine the time interval for which we have to determine this average velocity. No? So what we have is alpha, it is given, it is the acceleration, so it will be negative. So what negative means? Do you understand that? Suppose if I'll consider a particle going around in a circular path, suppose, and let's suppose for simplicity, it is undergoing circular motion about a circle whose center is the origin itself. And it is undergoing that circular motion in xy plane. So if I'll tell you that angular acceleration velocity at t equal to 0 is omega naught this way, so what will be our initial angular velocity? If we will consider writing it down in vector form, it will be omega naught into k cap. Now I want to reduce its angular speed. So what I must do? I must apply an angular acceleration which should be opposite to the angular velocity. So our angular velocity, it is having a sense from the side from which you are looking at it is anti-clockwise. And it is having a direction which is along plus z. Correct.
So Z means K cap only should come, sir.
So that's what now plus z. So now I want to apply some acceleration which should reduce the velocity. So the acceleration must be in opposite sense to whatever sense of omega I see from the same side. So alpha you see from that same side is clockwise, and the direction it is going to be having will be minus z. Correct. So you can see it is 1D only or
Minus K, sir.
1D only or not. In vector form, you see the velocity in k cap, whatever it is, and acceleration in minus k cap. So it is 1D. So in 1D, I told you we can avoid using k cap, j cap, and things like that, and we can just tell directions using plus minus. So whichever way our omega is now, if I consider that way to be positive, then alpha will be taken negative. That's why I'll write down alpha to be equal to minus of k root omega. And alpha we know it is also equals to d omega by dt. That is minus of k root omega. So what we do next, that is maths only. We separate the variables and then we integrate it. So d omega by root omega equals to minus of k dt. And we don't know what it is going to be at time t. So I'll assume it to be, suppose at time t, the angular velocity is omega. But we know what it is at t equals to 0, it is omega naught. And everyone can do this integral easy, no? It is omega to the power minus 1 by 2, and have to integrate it with respect to omega. So it will give us twice of root omega, limits from omega naught to omega, which is equals to minus of kt. So what we get is twice of root omega minus of twice of root omega naught equals to minus of kt. So from this we can determine how omega will be changing with time. But really we don't want that. What we want, okay, maybe we will determine that also. So what it is going to be, omega root omega will be root omega naught minus of kt by 2. So omega will be root omega naught minus of kt by 2 whole square. No. So I need to know when the omega will become 0. So if I equate omega to be equal to 0, what we get is at time t equals to 2 root omega naught by k, at this time the omega will become 0. So from this we know what is the time interval I have to consider. It is this only. No? Now next I need to know what angle it will cover in that time. For that what we do is we find out the angle it is going to cover, or else any idea what else we can do. So what we have is the
Sir, it
average,
is z-axis means we can take it
the
as
average angular velocity will be delta theta by delta t. Delta t we know it is our 2 omega naught by k. Now try to remember the graphs of motion from the earlier classes. So area under which thing was supposed to give us displacement? Area under velocity versus time plot used to give us displacement. Similar to here also. No? So what we have is I can write down omega equals to d theta by dt. So now if I throw dt to other side, what d theta is? It is the small angular displacement that you will have in a time interval which is very small, which is dt. And if I want to figure it out, the angle it covers in some finite time interval, I must integrate both the sides. For the given time interval t1 to t2, angle it was at theta 1 to theta 2. So what I get is theta 2 minus theta 1, which will be delta theta, is going to be integral of omega dt. It means the area under, whatever you need to find here, you can figure out by analogy also. Area under VT plot used to give us the angular displacement there. So area under what will come in place of velocity? Obviously angular velocity. So area under the angular velocity versus time plot will give us the displacement. No, area under omega
yes,
minus
sir.
t plot will give us the angular displacement. So it means in numerator I must be plugging the integral of omega with respect to time. Denominator we know what time interval in which it is becoming 0. So what we have is the average angular velocity will be integral of omega dt from 0 to t divided by this time interval t. And what it is? 0 to t omega root omega naught minus of kt by 2 whole square dt divided by 2 root omega naught by k. And this integral I think everyone can do. No? If you don't know what to do here, you expand it. That then it will become, every term will become something for which you know how to integrate. No? After this, I think I can leave it now. Or do you want me to integrate it? So this everyone can solve, no? Solve and tell me what answer comes. Everyone do it. I'll give you 2 minutes. You know what is to be done. Either you can use integration by substitution if you remember. Or if you don't want to go there, you just square it up. It will become omega naught plus k square t square by 4 minus of kt omega root omega naught. And that is something very easy to integrate also now. Maybe I'll write down here 0 to t omega naught, which is constant, minus of k square t square by 4, not minus, plus of, and then minus of k root omega naught into t by 2 root omega naught by k. So integral of this thing will become omega t plus k square t cube by 12 minus of k root omega naught into t square by 2 divided by 2 root omega naught by k, and the values are from 0 to t where t equals to 2 root omega naught by k. Plug the values and solve it. I think the answer will come omega naught by 3. Please tell me if you have any doubt.
No, sir.
So copy this thing, after copying tell me. Okay, I can take a new page.
1 minute, sir.
Okay, I can take a new page now.
Yes, sir.
Yes, sir.
Now see, whenever we define angular velocity, just like that, I can't ask you find angular velocity because it is always defined with respect to some point or not. So the rate at which, suppose if I ask you what is the angular velocity of any point is with respect to some point, suppose I want to figure out the angular velocity of the point P with respect to this point 2. So what basically we do is the rate at which the angle made by the position vector is going to be changing from what angle? The angle made by the position vector from the reference direction. The rate at which that angle changes, that is something which is going to be our angular velocity. No? So angular velocity is always defined with respect to a point from where we consider the position vector of the given point. No? Correct. So suppose if I'll give you that there's a point, see this thing I was going to do at the end, since these things are easy. Before that I was going to do, that's what is centripetal acceleration and things like that, but I did not see the attendance that I wanted, that's why I'm telling the things that are easier ones. Suppose if I'll give you, there's a point O, okay, and this is another point P. And here I'm telling you the point O is fixed in space, or it is in ground frame. And what is given is this point P is going with a velocity which is at an angle with the line joining these 2 points. So suppose if the point P is moving with a velocity V, which is inclined at an angle theta with the line, which is the line joining the point O and point P. And what we are trying to do is to figure out the angular velocity of P with respect to O. So tell me, one thing is that I can do is I can take component of this velocity along the line joining them and along perpendicular to the line joining them. Maybe I'll draw it properly, just a moment. So what I do is I take component of this velocity vector. This is our V, making an angle theta with the line joining the point P and the point O, where point O is the fixed point here about which we are calculating the angular velocity of point P. So if I take components, one component I'll write on as V perpendicular, that is going to be V sine theta in this case. And another one I'll write on as V parallel, that is going to be V cos theta in this case. Tell me, at any point of time, the separation between them is R. So the rate of change of separation is going to be equal to which velocity, whether it will be V sine theta or V cos theta. So how you will decide that? Suppose if I have a case where V perpendicular is 0. Suppose if I take a case where V perpendicular is 0, then what kind of motion I will have of P with respect to O? Tell me. So our point P will be moving this way only, no? So tell me, the angle that the position vector is making from whatever reference direction will not be changing at all, no? Correct. Suppose if I have a particle moving along x-axis only, and I took the origin to figure out the angular velocity. So the angle made by the position vector with the x-axis, the reference direction will never change, or from any direction it will not change. So in this case, our d theta by dt will be 0, no? And at any point of time, the separation is r. So what we have is, in this case, our dr by dt, the rate at which that separation changes will be v only, or not? Now, next case, if I take where our v per, so this case is v, sorry, by mistake I wrote v perpendicular is 0. Next case, if I take v parallel is 0, it means whatever velocity I see of p by sitting in the frame of O, it's going to be only along the line joining, only along the direction perpendicular to the line joining OP. Now, in this case, you can tell that dr by dt will be 0, no? And the only thing that our point P does is to go around and see. Point P is neither moving towards O, neither it is moving away from O. So what exactly it is doing? It is just going around O or not? Tell me. So after some time, if I see what is the velocity will be still perpendicular to the line joining them, it is going around the point O without going away from it, without going towards it. So in this case, the rate at which this angle will change, suppose I want to determine that. So what I will do, I will consider the angular velocity in this case will be our V perpendicular, which is going to be V only by R. So in general, what we do here, if I have to write down the angular velocity of the point P with respect to O will be our V perpendicular by R, where V perpendicular is the component of the velocity perpendicular to the line joining them. I'll zoom it here a little bit. Where V perpendicular is the component of the velocity perpendicular to the line joining them, and R is the separation between them at that instant. No? I hope you got the idea what is to be done to figure out the angular velocity of any point which is moving with respect to some another point which is stationary. So in general, two things a particle can do with respect to some fixed point is it can go around that point or it can move away or towards that point. So if I consider the point P to be at some distance r from our fixed reference point and making an angle theta with the reference direction, so r can change, theta can change. Suppose if r not changing, only theta changing, when it will happen? That will happen when the velocity of the point P must remain perpendicular to the line joining OP all the time. Correct? That you get that, no? So when I have got the velocity not perpendicular, then what we do? We'll find the component of the velocity, the one that is perpendicular, because this component of the velocity is the only region because of which theta will change. Tell me V perpendicular 0, the theta will change, no? So how much it goes around that point angle wise, that will be decided by the component of the velocity, the one that remains perpendicular, is it not? Correct. So copy this thing everyone. All of you understood now? I could have come to this point in different manner before, after telling you centripetal force and things like that, but since many of you are absent, so I'm telling the easy things before. The more complicated things I'll talk in the offline class. Anyone having any doubt about it? And what is our omega PU that you got, no?
Sir,
Yes, tell me.
sir, here it will be a case of V parallel now, sir.
Which one? This one V perpendicular 0, so only it will have is V parallel. And
No,
we
sir.
have
When only angle changes, then it will be a case of V parallel now, sir.
what V parallel must be 0, no? R
Yes,
not
sir.
changing, only angle changing. Then whatever velocity it will have must be perpendicular to the line joining them.
Yes, sir.
So in that case V parallel will be 0, no? And velocity will be only lying in the direction perpendicular to the line joining them.
Okay, sir.
We can prove it also in this one way. What we can do is, suppose if I consider the particle to be moved around that point through in a very small time interval. Now, if I consider the time interval to be very small, so what we have is, suppose in that small time interval, it covers angular distance d theta at its center of rotation, and the distance it covers is suppose dl. So dl is the distance it is moving perpendicular to the line joining them. And if I take a very small change in the time in that, what the dl I can write down as the speed with which it is moving along that curved path will be the velocity that will be along the tangent or not. See, I am going away from this point Suppose if I'll give you this case. Suppose if I'm going away from this point as well as I'm going around this point. So how much I have gone around this point, because of which I will cover some length, correct? And that length dl will be equal to v perpendicular into dt or not? Understanding this point, how I wrote dl as v dt. I have got some point going around another point. So how much whatever velocity it has got along the tangential direction, that will decide how much it is traveling along that tangential direction. Getting that point? Because this particle is not going around in a straight line path, it is going around some curved path. So what velocity it has along the curve, that will decide how much distance it has traveled in a small time. So that small distance it covers, dl I can write down as v perpendicular into dt. And in that small time interval, I can consider r to be not changed much. So radius will be almost same only. So if I give you angle in radians, then you can find arc length or not. So that dl will be equal to also equal to r d theta. And that we know it is also equal to v perpendicular into dt. So what we get is r into d theta by dt becomes equal to v perpendicular. So from this I can write down d theta by dt, which is omega, that will be v perpendicular by r. Now you got it now?
Yes, sir. Now I got it, sir.
This thing would have been more easier to understand if I would have taken the derivation that I will do regarding that centripetal acceleration and all. Since people are absent, so I took this thing first, because if anyone will miss this, he can manage. But if anyone will miss the other thing, it will become very much impossible to manage. Copy this thing. Then we will see what is to be done in case if I have got both the points moving from the ground, moving as seen from the ground frame. No one is having any confusion why I wrote TLS PDT, because I'm considering a very small time interval first of all, and the velocity vector will be tangent to the velocity vector which is along this path will decide how much it has traveled along this path, and the velocity vector will be along this path is going to be the one that is in tangential direction, and that will be the one that is going to be perpendicular to the radius. So the velocity that will be lying along that path is going to be our v perpendicular. So how much it has traveled is going to be v perpendicular into dt. And in doing so, it covers a small angle d theta, considering r not to be changed much because dt very small. So that dl we can write it down as r d theta, which is also equal to v perpendicular into dt. So that will give us the omega will be equal to v perpendicular divided by r, where v perpendicular is the velocity that is perpendicular to the line joining these 2 points. Copy after copy, tell me. Okay, I can take a new page.
Yes, sir.
Next, suppose if I'll give you 2 points which are moving as seen from the ground frame. Suppose one of them is moving with V1, making an angle theta 1 from the line joining them. Suppose if this point is A and this another point is B. And this is moving with V2, making an angle theta with the theta 2 with the line joining them. So what we will do, we'll take the components of their velocities along the line joining them and perpendicular to the line joining them. A similar thing we have done earlier also, if you remember, when we were finding out the rate of change of separation between two moving particles. Remember that one? This will be V1 sine theta 1. Similarly, here I have V2 cos theta 2 and V2 sine theta 2. So V2 cos theta 2, V1, sorry, not V1, V2 sine theta 2. Now suppose if I want to figure out the angular velocity of B with respect to A, it means I will be sitting in the frame of A. So if I am going to be sitting in the frame of A, then whatever velocity I see for A will be 0. And whatever velocity we are going to see for B will be the relative velocity of B with respect to A. Correct. So if I will draw this thing, I think everyone can understand that. I'll sit in the frame of A, what all velocities I will be seeing for B along the direction perpendicular and parallel to the line joining them will be B2 sine theta 2 minus of B1 sine theta 1. And the velocity that it is going to have along the line joining them, I'll write it down as B parallel. That will be V2 cos theta 2 minus of V1 cos theta 1. Now, at any point of time, suppose the separation I have between A and B is R. So what exactly will be the rate of change of that R? That will be dr by dt, and that is going to be equal to V2 cos theta 2 minus of V1 cos theta 1. And that I will write it down as the V parallel relative. And you get that, no? What V parallel relative is? It is the component of the velocity of B along with respect to A along the line joining them, no? It is the relative velocity of B with respect to A along the line joining them. So like the way earlier our omega, how we got that? By finding out the velocity of B that we see which is perpendicular to the line joining the point O and the point P. Same way here, the angular velocity of our particle B with respect to A will be how much it is going around the line joining AB will be decided by which velocity, the one that is lying perpendicular to them or not. So omega of B with respect to A here will be V2 sine theta 2 minus of V1 sine theta 1 divided by the separation that I have got between them at any point of time, suppose R. So what exactly it is? It is the angular velocity of B with respect to A. And how much it is? It is the component of velocity of B with respect to A along the direction perpendicular to the line joining them divided by the separation between A and B, whatever we are going to have at that instant. No? If it changes, so omega will also change. I hope you got it, how to figure out the angular velocity of some point with respect to some point which is stationary, or even with respect to some point which is moving. Try this question as a homework. Two points are moving with uniform velocity u and v along the perpendicular axis ox and oy. The motion is directed towards O, that is origin. When t equals to 0, they are at a distance a and b respectively from the origin O. Calculate the angular velocity of the line joining them at time t so that it is greatest when t equals to this much. Okay. So try this question as a homework. From here, we will continue in the next class.
Sir, can you please post today's lecture and previous class lecture in Google
Previous
Classroom?
class, November 12th lecture I have posted, okay, with video. Okay, others I will post today. Okay.
Okay, sir. Thank you.
Google Classroom you can check that, but audio is not good. Try to manage that. Depends upon the recording. No, audio is not good. I
Okay,
don't know
sir.
why, but try to manage from that. This date is 19th November.
Thank you, sir.
Okay, bye. All of you, those who have
Thank
copied
you, sir.
can leave. No problem.
Thank you, sir.
Amen.